Welcome to function and Taylor series equality. So recall in the previous video, we wondered when a function was equal to its Taylor series. And essentially, since the Taylor series is the limit as n goes to infinity of our Taylor polynomials, essentially we just need the error to go to 0. Right? So recall that we had that f of x was equal to p n of x plus r n of x, where r n was the error. Right? So our theorem, recall for f infinitely differentiable. So for f for which all of the derivatives, right? So the nth derivative exists on I for all n, right? And for x equals c, right? We had that f of x was equal to p sub n of x plus r sub n of x, where p sub n was the nth Taylor polynomial. At c, and r sub n of x is the error. And we had that r sub n of x was bounded, right? We had that absolute value of r sub n of x was less than or equal to the max of the absolute value of the n plus first derivative evaluated at z, all over n plus 1 factorial times the absolute value of x minus c to the n plus 1, right? Essentially what we need is we need these errors to go to 0. And if the errors go to 0 for all x in I, then we have f of x is equal to its Taylor series on I. So if our R sub n of x's go to 0, so in other words, if the limit as n goes to infinity of R sub n of x is equal to 0, then I should say is equal to 0 for x in I, or for all x in I. Then f of x equals its Taylor series. So it equals the sum from n equals 0 to infinity of the nth derivative of f evaluated at c over n factorial times x minus c to the n on the interval I. So again, this idea I was mentioning previously, essentially, we just want the error to go to 0. If the error goes to 0, that must mean that the polynomials are approaching f, right? So if that error goes to 0, then our function is equal to its Taylor series. So first off, let's go ahead and show that f of x is equal to e to the, f of x equals e to the x is equal to its Maclaurin series for all x. So essentially what we need to do here is we need to show that R sub n of x goes to 0 for all x. Right? And to do this, what we can do is we can show instead that the absolute value goes to 0. So instead, or to do this, we will show that the limit as n goes to infinity of the absolute value of R sub n of x is equal to 0 for all x. And all we need to do for that is to show that it's bounded above by a sequence that goes to 0. So we can do this by showing that the absolute value of R sub n of x is bounded above by a series, or by a sequence, sorry, that goes to 0. So to do this, we will use that bound that we have. So we will use the fact that absolute value of R sub n of x is less than or equal to the max over I of the absolute value of the n plus first derivative of f. Take that max, divide it by n plus 1 factorial, and then multiply it by the absolute value of x minus c raised to the n plus 1. So here our c equals 0. We are doing a Maclaurin series. So we know our c is equal to 0. F of x equals e to the x has great derivatives, right? So we have c equals 0. The n plus first derivative of f evaluated at z is simply e to the z. So we can simplify this a little bit. So we have the absolute value of r sub n of x as less than or equal to the max of the absolute value of e to the z, which of course e to the z is already positive by default. Sorry, that was a sloppy z. And then that's over n plus 1 factorial. And then we're just multiplying by the absolute value of x raised to the n plus 1. So note, our interval just needs to contain both x and c. So our interval I, so the interval I just needs to contain x and c. So, and in this case, it's c equals 0. So what we can do is we can just pick an a that is less than both x and 0. So we will pick a less than x and 0. And we can set I to be the interval that includes a and then goes up to infinity. Sorry, I want to pick a greater than. I keep thinking of e to the negative x. So let's swap what I just said. For e to the x, we should pick I that goes from negative infinity up to a, including a. Sorry about that. So essentially, we're just going to pick something just past x, and it'll be some a, right? So e to the x, or e to the z, looks like this, right? So its maximum, if we're looking just over up to a, right? The maximum will occur at a. So the max of the e to the z over the interval negative infinity to a is simply e to the a. And I need to give myself a little more space. Okay, so we have that max, therefore, over our interval is e to the a, which we can just set equal to m. So this becomes that our absolute value of r sub n of x is less than or equal to m over n plus 1 factorial times the absolute value of x raised to the n plus 1. Right? Now, the sequence on the right, as n goes to infinity, this sequence goes to 0. So as n goes to infinity, this bound goes to 0. We could show this using the ratio test. So because that upper bound of a positive sequence is going to 0, then we know that the sequence itself is going to 0. So this tells us that r sub n of x goes to 0 as n goes to infinity. And that therefore tells us that f of x is equal to its, so our f of x equaling e to the x is equal to its Taylor series or Maclaurin series from n equals 0 to infinity of 1 over n factorial e to the x. Note that none of this depended on the value of x. So for all x, we can use this fact, right? And then we can just pick our a accordingly, depending on which x that we are using. All right. Now let's take a look at a Taylor series instead of a Maclaurin series. Our job is to show that f of x equals 1 over x is equal to its Taylor series at x equals 1 for all x in the open interval from 0.5 to 1.5. Just a quick comment. Note, it may equal its Taylor series on a wider interval. But it is easiest to prove on this narrow interval. So on the interval from 0.5 to 1.5. So once again, we'll go ahead and just set I to be the open interval from 0.5 to 1.5. Right? We have our C is equal to 1. We have our f of x is equal to 1 over x. Right? And essentially, we will use, for any x in 0.5 to 1.5, right? We have that the absolute value of r sub n of x is less than or equal to the max of the absolute value of the m plus first derivative of f over the interval I over n plus 1 factorial times the absolute value of x minus 1 raised to the n plus 1. So recall from the previous video, that the n plus first derivative of f of x equals 1 over x is equal to, or in this case, the of 1 over z. This derivative is equal to negative 1 raised to the nth power. Actually, let's do the nth derivative. We'll get to the n plus first derivative. So the nth derivative of f evaluated at z is equal to negative 1 raised to the n times n factorial times z raised to the negative in parentheses n plus 1. So this means that the n plus first derivative evaluated at z should be negative 1 to the n plus 1 times n factorial times z raised to the negative n plus 2 when we plug in n, That should be an n plus 1 factorial, not an n factorial. And that means that the absolute value of the n plus first derivative evaluated at z should be equal to n plus 1 factorial times z to the negative n plus 2, or times 1 over z to the n plus 2. On the interval from negative 0.5, sorry, from positive 0.5 to positive 1.5, right? The largest this can possibly, or this gets no larger than if we plugged in 0.5, right? We want as small of a denominator as possible. So on the interval from 0.5 to 1.5, this is no larger than n plus 1 factorial times 1 over 1/2, or 0.5, raised to the n plus 2. So what we get then is that the max of the absolute value of the n plus first derivative is essentially is no larger than, or is equal to, n plus 1 factorial times 1 over 0.5 to the n plus 2. So going back to our original bound, we have the absolute value of r sub n of x is less than or equal to, we have an n plus 1 factorial over 0.5 raised to the n plus 2. That's our max, all divided by n plus 1 factorial. And then we're multiplying by the absolute value of x minus 1 raised to the n plus 1. So this is the same as absolute value of x minus 1 raised to the n plus 1 over 0.5 raised to the n plus 2. But note, our x's were all within 1/2 of 1. Okay. But for x in the interval from 0.5 to 1.5, right, we have that the absolute value of x minus 1 is less than, not less than or equal to, is less than 0.5. So this statement that I've written above, we could have rewritten this as the absolute value of x minus 1 over 0.5, all raised to the n plus 1, times one more copy of 1 over 0.5. So since absolute value of x minus 1 is less than 0.5, that means that the absolute value of x minus 1 over 0.5 is less than 1. So we could apply the root test. We could apply various things. By the root test, we will wind up getting that this upper bound does converge. It will in fact go to 0. Right. This is behaving like essentially like a geometric series with r less than 1. So we get then that our absolute value of x minus 1 over 0.5 raised to the m plus 1 all times 1 over 0.5 behaves like a geometric series. Or is a geometric series, it doesn't even just behave like, is a geometric series. With absolute value r less than 1. A geometric sequence, I apologize. So it is a geometric sequence with absolute value r less than 1. It will head to 0. Right? You don't even need that part. We just know that it goes to 0. And so what we wind up getting then is that our r sub n of x goes to 0 as n goes to infinity. And so we get that our f of x equaling 1 over x is equal to the sum from n equals 0 to infinity of the Taylor series was -1 raised to the n times x minus 1 to the n. And this is on at least the interval from 0.5 to 1.5. As a note, just a side note, f of x does not have to equal its Taylor series on the entire interval of convergence for the Taylor series. So f of x may not equal its Taylor series on the entire interval of convergence. So just because the Taylor series convergence doesn't mean it necessarily has to be equal to, just because the Taylor series converges doesn't mean it necessarily has to be equal to f of x. All right. So this is sort of how we can go about verifying that a function equals its Taylor series. I should say, when I mentioned earlier that we could use the ratio test, if we have the ratio test shows convergence of that series, the sequence by default has to go to 0, because if it doesn't go to 0, the sequence diverges. And so I should have mentioned sort of here, if the series converges, that's really crowded. Let me make a smaller pen so it's not as sloppy. All right, so what we have here is if the series converges, the sequence must go to 0. So similar thing on this one, we could have pulled, again, we could have pulled the root test. Sorry, where was it? We could have pulled the root test here and said, well, the series of this must converge, therefore the sequence must go to 0. But that is showing that a function is equal to its Taylor series.